Committee for Elevators and Escalators of the National Building Code of India. He's also a member on the Indian Standards Committee and the Working Panel for Elevators and Escalators. He's an elevator consultant and is certified by the International Association of Elevator Consultants. He's a chartered engineer by profession and has a postgraduate degree in business administration. So over to you, sir.
Good morning. Like I keep saying that I would love to have been sitting across, seeing you all physically, but when we can't do that, we have to do what's the next possible. So what I'm going to do is I will get off my video also so that I can focus on it. Otherwise, there's something that comes on the screen. So I am taking my video off and let's start. Okay. Thank you very much for this opportunity, and let's see what we can do in 1 hour. I do conduct a workshop like this for architecture students, and normally takes 4 hours. Today, I'm going to try to compress into 1 hour what I would normally do in 4 hours. Let's see how it goes. Tall buildings has been something that has always been an ambition that people have had. I mean, for instance, today we have the Great Pyramid, which still stands at 146.5 meters. Lighthouse of Alexandria at 140 meters, which has been doesn't exist anymore. But if you look at the Great Pyramid, it is from 2560 BC. That's like 5,000 years back, almost 5,000 years back. And if you look at from an Indian perspective, we have had tall ambitions. The Qutub Minar at 72.5 meters was the tallest structure in India till Usha Kiran was constructed. Usha Kiran, I believe, is at 74 or 76 meters. But even at that point of time, if you look at 1316 AD, there was another structure in front of Qutub Minar, which was planned at 145 meters, which didn't get completed. So we seem to have something that continues with us in history. We also do have projects like that, which we plan out in India even today, which don't get completed. So tall has always been the case, and if you look at prehistoric times, there's a reference in the Bible. It's referred in other religious books too. They talk about the Tower of Babel, and what it says in the Bible is, and they said, let us build us a city and a tower whose top may reach unto heavens. So the point is that tall ambitions have always existed. So let's just have a look at how tall this building could have. And because it's a prehistoric kind of a scenario, we will have to refer to historians or experts as to what they have to say. So there is a book, Structures, by Professor Gordon J.E., which says all white things don't fall down. And in his opinion, this building could have been about 2 kilometers high. And in comparison, the Sky Mile Tower, which they are talking about Tokyo completion expected 2045. I don't know how many. I'm not too sure that I would be alive at that time. The Kingdom Tower, which is under construction, which is supposed to be completed in 2018, which is still not complete, is all much smaller. So again, the fact of the matter is ambitions have always been there. People have always been constructing. So then the question that comes up is, so what's the big deal in tall? Visualize prehistoric times, they were talking about something that was 2 kilometers high. So what's the difference? We have the Qutub Minar, which was at 62.5 on the left, and we have Usha Kiran, which went taller than Qutub Minar after close to 500, 600 years. So what's the difference? So if you look at Wikipedia, it difference in architecture, construction, engineering. The difference between a building and a structure is that a building will support continuous occupancy. So a building definitely is a structure, but all structures are not necessarily buildings, because if it doesn't support continuous occupancy, it's just a structure. I mean, just like the Qutub Minar, it is not expected to support occupancy. So what makes the difference? So again, if you look at Wikipedia, it says that in the 19th century, buildings of over 6 floors were rare, as having climbing floors was impractical, which I think is an obvious scenario. I do know that many colleges, many schools which are multi-storied, when it comes to elevators, they don't include the students, and the students are expected to climb up stairs, which probably is good for health, but not necessarily a right way of designing a building. Then if you look at what happened is in 1853, Elisha Greaves Otis invented the safety elevator. And this is an exhibition which happened, and what he would do is he would get on the platform, he would cut the rope, and the rope would not fall because he had invented a safety mechanism to ensure that the elevator doesn't drop. After 160 years, the same technology, the same approach, the same concept still exists for safety of elevators. And for all practical purposes, it's Elisha Greaves Otis's invention that made it possible to construct buildings that were tall, because then people didn't need to. There is Ms. Chaudhary, I believe, who is asking for control of the screen. Should I? Hello, excuse me. There's somebody who's asking for control of my screen.
No, go ahead.
No,
yes,
sir.
Please. Yes, please.
Okay, you can see my screen, right?
Yes, we can see your screen, and go ahead.
Yes.
So after the RCC and the structure, what happens is, what is most crucial is the vertical transportation structure. Unfortunately, and I say this from experience, I've been a consultant for the last 16 years. I sit through design meetings, and it's a sorry state of affairs where even toilets, horticulture, landscaping get a higher priority than the elevators. Now, as we go along, I will give you proof as to why I say this and why I would talk about this. So, I'm a civil engineer by qualification who's got into an electromechanical line, and I know for a fact that if your structure is not right, your foundation is not right, you do not have adequate reinforcement, your RCC is wrong. For all practical purposes, you have to bring the structure down. I'm not talking about the old Mumbai area where you can put up a couple of scaffolding and keep the structure up. I'm not talking about that. I'm talking about a tall building. What would you do if your elevator core is wrong? Can you add elevator cores in a building? Again, I'm not talking about a small building where you put in an elevator between the stairwell or you have something which is added on externally. I'm talking about a tall building. Invariably, the answer for both is that you have no alternative but bring the building down. So let's look at the cost of inadequate elevatoring. Now, over the last 6 months, and we do this often, we are approached with cases where people tell us that, okay, we have a problem with the elevators. There are long waiting periods. Can you do something about it? And 99.9% of the cases, we don't have a solution. This is just to give you an example of it. I mean, these are 5 buildings that we have been working on over the last 5-6 months. And the client got very upset with us because we didn't have a solution. So look at building 1, 2,700 population. The average waiting time is 323 seconds. That's 5 minutes. Now, I know there are people who say, oh, what is so great in 5 minutes? But if you were to convert that in a commercial building into time over an annual, you're talking about a cost of about 3 crores every year. Now, these buildings that we are talking about are buildings that have been in existence for over 10 years. And this is fairly distributed over this city. I've just picked up this city as an example. So if you were to look at it, look at the worst case scenario, 15 crores. 15 crores into 10 years is 150 crores. The cost of that building was probably only 500 crores. So the loss in terms of hours to the tenants, to the people who are there, is in multiple crores. And we need to recognize that in these situations, there's really nothing that can be done. I'm sure that I don't need to give you elaborate as to which are these buildings. I'm sure you've seen these buildings. And in February this year, now I was part of a panel discussion, and one of the questions that I asked was, how many buildings in India actually have a design basis for elevatoring? We had a lot of discussion amongst the panelists. There were some thoughts. And finally, we came to the conclusion that not more than 10% of the buildings in India would have a design basis for elevatoring. More or less, everything is based on thumb rules. So, elevatoring is all about converting structures into buildings. Now, as architects, do you want to be just doing structures? I mean, do you want to just build a Qutub Minar, or do you want a building? Now, if you want a building, it is about elevators. And here ends my first lesson. And if you were sitting face to face in a classroom, I would say that, okay, the rest of the lessons are not important. If this lesson has been put across, if I have managed to get this message across to you, the rest of it is not that critical. So you are at home, you could probably turn on to Netflix, you could turn on the rest of the things are not that critical. This is the most critical. This is 99% of what I would be talking about today. For those of you who still are continuing, I'll get into a little bit more of detailing. History of lifts. Yes, we have had lifts before Elisha Greaves' invention. However, they were more for people, for goods, because it was unsafe. So if the ropes got cut or there was a failure, it would collapse. And it is Elisha Greaves Otis who made the difference. I did mention about this is his 1861 patented drawing, All Safe Gentlemen, and that is where the skylines of this world started changing. There were hydraulic lifts, 1870, 1880, electrical lifts. Everything sort of slowly started falling into place after 1853 and started getting taller and taller. Again, a clarification, lifts and elevators, they are the same thing. The British talk lifts, and because we are a British colony, ex-British colony, we refer to lifts. So if you look at the standards, it's lifts. However, both these are synonymous, and in fact, Otis would refer to as elevators, Coney would refer to as elevators, and most elevator companies would also refer to themselves as elevator companies and not lift companies. But these are the same thing, makes no difference. Talking about just few things. So you have on the extreme left is what is referred to as a machine room elevator, where you have equipment tucked up in the machine room. What you have in the middle is a machine roomless elevator, which is just about 20 years old in its invention. And then you have the hydraulic elevator. Now, the difference between these three and its application and its pros and cons is something which, again, is a 1 hour session, which I will not be covering today. But it's essential that you understand what a machine room elevator means, what a machine roomless is, and what a hydraulic elevator is. I mean, all three are very different in its approach. Some of the components, I've told that you know the components, but the point that I'm trying to indicate is that today, when we put together these components, or when you are designing an elevator or you're designing the elevator machine room, remember, it is not just a question about the functioning of the equipment. We also need to remember that for the next 20, 25 years of the life of the building, this equipment needs to be maintained. So you also need to provide adequate space for the engineers or the technicians to be able to maintain the equipment. So now, for instance, if you were to look at this machine room, you'll see that, oh, there's a lot of free space. Can I make the machine room smaller? To get the elevator operational, yes, you could make it smaller, but to maintain it, you would need to have adequate space. So when we talk about designing a building, I mean, I keep saying that there are three distinct phases in the design of a building. First is the area where you do the design criteria and the analysis. Then you get into architecture interface, and then you do the specifications. And this is a significantly iterative process between the design criteria and analysis and the architectural interface. It's a fairly iterative process, and it is also indicated in the National Building Code. We will discuss it as we go along. So what we'll do is first we'll talk about the design criteria and analysis. Again, remember what I'm talking about. We'll be talking about it from a surface level. We will not be able to go into significant in-depth discussion because of the time requirements. So if you're talking about the detailing that is required, of course, you need to define the building. If it's a hospital building, or it's a hotel, or it's a commercial building, or it's a multi-use where you have residential apartments on some floors, a hotel on some floors, commercial, the entire approach is different. You need to be asking enough questions. So often when we get into a design, they said, why don't you give us a checklist? And I'm very, very hesitant to give checklists because checklists sort of box in the answers that you would get. I would prefer a free-flowing discussion to understand what all is involved. So if you were to talk about a building, hotel building, whether super premium, where is the location, all these things make a difference. It's a single tenant, multi-tenant, and of course, try to anticipate the unknowns. There's always this question that comes up, but how can we anticipate the unknowns? But if you ask adequate questions, there are a lot of things that would sort of come out. Could somebody have predicted the COVID? Probably not. But there are many things that we can anticipate, and we need to define that. When we talk about population, the number is a crucial aspect, and that is where normally there is a huge gap in terms of understanding. We need to remember that there's a difference between the numbers that you would consider for HVAC or floor loading and the numbers that you would consider for elevators. You need to understand demographic profile, the cultural background. uh, if suppose a building is a residential building and it is being designed in the US, in Manhattan, for instance, it'll be very difficult for them to understand the fact that in India, I'm not talking about today, but otherwise newspaper and milk gets delivered to our doorstep. So if an architect based in the US with that Manhattan experience were to come and design for India, he would not provide for the service staff or the service requirements that we would have. So these are all things that you need to do. And again, unknowns, again, you need to keep asking questions as to what all could possibly happen. And when we talk about material and service, this is mostly ignored. And what invariably happens is that, okay, we need to provide a service slip or we need to provide something for a stretcher. So let us provide something in. But that's not adequate because you would need to check with MEP. You would need to check with the services as to what is the largest equipment in terms of volume, in terms of weight that needs to be carried up. What other equipment do you expect to carry up into the building? Now, the taller the building, the more difficult it is. Yes, here today we have Mathadi workers who will help carry stuff up. But if you're talking about 70 floors or 80 floors, even the Mathadi workers would probably have a problem. My daughter, she plays the piano, and somewhere on her 15th or the 16th birthday, my mother presented her a piano. And we struggled to get it up into our 4th floor apartment. So these are the things that you need to keep in mind. And remember that, again, what I keep saying, that if you have designed it wrong, you have to live with it for the life of the building. Okay. Now let's get into some parameters that are used. I refer to this caution. This is Dr. Gina Bani. She is probably 80 years plus, a lady who has devoted her life to elevators. She was an electrical engineer, and her book, The Elevator Traffic Handbook, is virtually a Bible for traffic analysis and design of elevators. And she makes it very clear that just because you've read the book, you will not become an expert. You need to spend time to understand the theory, which is very complex. It's not a thumb rule basis that you can establish elevators. It's not that you toss a coin up in the air and say that, okay, this is what it is. It's not that you say that, okay, that building had 3 elevators, so let me do 3.5 elevators here. No, there is a lot more that goes into establishing the elevators. So I sort of add on a little bit to what Gina Bani has said. I say that this session will also not make you an expert. It'll just give you an indication of the question that you should probably ask or what you need to be aware of when somebody comes and gives you a traffic analysis report or a design basis report for elevators. So there are 2 things which in the classical mode are always talked about, handling capacity and interval. I do not know how many of you are aware of this, but let me just sort of take you through it. Handling capacity, simply put across, is what the elevator system can handle in a specified time with a specific average loading. And the specific time interval is invariably 5 minutes. 5 minutes is because it was a convenient thing, because 2 minutes is too less and 10 minutes would have been too long. So 5 minutes is considered as a time, and the average loading is considered to be 80% or less. Interval is a time difference between 2 elevator departures. We will come to that again, and that recognize very clearly this is not average waiting time. This is the time difference between 2 elevator departures. And both are derived from the round trip time. Now, I mentioned this very clearly that this is the classic approach, and this is a classic approach that has survived for more than 60 or 70 years now. And it is the only way we can do an apple-to-apple comparison between 2 calculations or 2 buildings. So the round trip time, a formula. Don't try to mug up this formula. Try to understand the components that are involved, what makes the difference. So you have 2H. H is the average highest reversal floor, and S is the average number of stops. So why is it 2H? It is that the elevator has to go up and come down. So the time that it takes to go up and the time it takes to come down. Now, TH is the time that it would take for a single floor transit. So if the average flows is 60 and a half, it would be 60 and a half into the single floor transit time. S plus 1, S is the average number of stops, and 1 would be that the elevator goes from the lowest floor, the acceptance floor, and then it goes up, and then stops at all the various floors, and then comes down. So that is the S plus 1, and the TS is your door operating time and the loss on account of each stop. Then 2 into P into TP. P is your average passengers that are carried, and invariably it has to be 80% or less. One, it is from a formula perspective. Second is we need to remember that when we talk about elevator loading, we are talking about 68 kilos per person. So somebody like me is definitely more than 68 kilos. So if you were to design on 100%, we'll invariably have a problem. Now, the 2 into TP, the transfer time, the 2 is people going in, that is 1. People coming out, that is 2. So that is the 2P. So you recognize, so the more number of floors, the higher is going to be your impact on account of age. Higher is going to be impact on account of the number of stops. And larger the car, higher is going to be the impact of your people ingressing and egressing from the car. So H and S are the statistical functions. Again, please don't worry too much about this formula as such. If you ever are interested, please refer to Gina Bani. She would. Her book is pretty detailed. In fact, I keep saying even today that if I'm a little bit of a problem sleeping, all I need to do is pick up that book and start reading, and it puts me to sleep very fast. Again, what you need to remember is what are the implications. So higher the building, the more number of stops, the bigger is the impact of H. Higher your car capacity, bigger is the impact of the probable number of stops. So for instance, if you have a ground plus 1 building, the number of probable stops is 1. Your H is going to be 1. If you have a 1 passenger elevator, again, your probable number of stops are 1. So you need to recognize that these are all an iterative process. So more stops, you have a problem. Larger the capacity, you have a problem. And you need to ensure that this is balanced. H and S, obviously, it is not a function of speed. It is not a function of your door opening or door closing time, because it is just a function of your average car loading. It's a function of your number of stops. So, so if you were to take a 20 number of floors as 20, and suppose we have a 10 passenger elevator, the average loading is 8 at 80%. So you have 18.2 possible stops. Reversal flows will be 18.2, and your average number of stops will be 6.7. So irrespective of who calculates it, H and S will not vary because it's something that can be extracted from our table. There could be differences on the rest of the components, because I could anticipate and say that, okay, well, this building is of older people, so they will take more time to ingress or egress. Maybe it's an old health home. Or on the other hand, it's a college institute where people will be snappy in getting in and out. So there could be a difference in your time components or your time assumptions, but it cannot change. This particular aspect cannot change. So from round trip time, where do we get into? We do the up peak handling capacity. It is 300. 300 is 300 seconds. That is the 5 minutes divided by round trip time, which means in 5 minutes, how many times can and the elevator go up and down into your average loading into L. And this is expressed as a percentage of your total population. And your interval is the round trip time divided by L. Now, what is key here is that, again, remember, these are statistics. These are all permutations, combinations, probabilities that are involved. It is the number of lifts in the group. So if you have 8 lifts in 2 different corners, your round trip time is not your interval is not round trip time divided by 8, but it will be round trip time divided by 4. Keep this in mind when we often have had this problem where we come up with a recommendation saying that we need 8 elevators. The architect, from a perspective of how the building should look and all, divides his 8 elevators in 3 different corners or 2 different corners, and then we end up having a problem because it doesn't give you the same results. I hope that you can read this. This is an extract from the National Building Code to sort of indicate the limitations of the classic thing, or rather the assumptions which go into doing this. So in many ways, the traffic analysis is based on an ideal condition. So it assumes it's a pure a peak. That means the people are picked up on the ground floor and then they are rushed up to the upper floor. They drop to the upper floors and the elevator rushes back immediately. Even if there are 3 people who decide to go from an upper floor to an intermediate floor, we have a problem. It's assumed as a rectangular distribution formula, which means that every time the car is filled to an average of 80%, which again we know doesn't happen. It's always a bell curve. Floors are equally populated. Again, is not the case. In the floor heights are equal. So the reason why I'm saying this is you need to remember that when you do the traffic analysis, there's already an idealism that is assumed. So if at that point of time we say that, okay, let us compromise a little on basis of the traffic analysis, like say, for instance, I need a handling capacity of 10% and say, no, we are okay with 8 to 9. We need to remember that the 10 itself has been arrived based on an ideal assumption. Things that we need to remember, handling capacity is what the system can handle. Arrival rate is what will actually happen in terms of people reaching the building. Unfortunately, in the elevator industry too, there are people who interchangeably use this. Remember very clearly that what we need to achieve is a system can handle so much and so many people arrive. And what we should try to do is try to ensure that this is matched. But in any case, we have norms that have been set up for a commercial building. For instance, your multi-tenant building, you need to have an minimum handling capacity of 10%. So though people are arriving at different times in the morning, we need to remember that lunchtime people would be together. And in any case, if this building is located near a metro station or near a expressway where traffic can reach fast, we probably need to plan on a higher handling capacity. And if it's a single tenant building, definitely it has to be more because the possibility of a diverse arrival rate is going to be significantly less. So these are things. I'll just come to this particular thing in terms of what everybody asked for. A quick look into interval. Remember, it's again a statistical function. So if you focus on the red car, 30 seconds to go to the halfway point, 1 minute to get to the top point, and then 2 minutes to come to the bottom. So if you were to look at it from that perspective, the round trip time of the red car was 120 seconds. Because there are 4 cars, you divide by 4 and you get an interval of 30 seconds. The reason why I'm showing this is for you to understand what is the difference between interval and average waiting time. So the interval is the time difference between 2 elevator departures as an average. So if you were in a scenario where you didn't have enough elevator cars, you could have an interval which is very good, is awesome, but then you have an average waiting time which is higher with people still waiting in queues. And the classic example that we have would be the Cup Parade and Nariman Point area where you have smaller cars and the interval is very fast, elevators come down, but you are still waiting in a queue. We need to recognize, like I said, the average waiting time is not the interval. Again, something that is often confused. Interval, let me repeat, is again the time difference between 2 elevator departures, while average waiting time is the time that somebody will have to wait after the first button has been pressed. If it is a conventional system, there's an up and down arrow, or after the person has arrived at the landing, assuming that the button has already been pressed. Now, just to sort of understand how it works, what we did is we calculated the conventional classical way, the handling capacity and the interval. Now, how does that apply to a person? So if we have 2 people arriving, Raghu arrives, Anita arrives, and they push the button, the elevator comes in. So if you look at it, Raghu's waiting time is larger than Anita's waiting time. This is what invariably happens. Now, Anita should be a happy lady because she is had to wait very less. Now, Raghu's time to destination is lesser than Anita's. Why? Because Raghu is on a lower floor. And Anita's time to destination is larger. So the reason why I'm showing this is because we might do the calculation and find that we have a good acceptable handling capacity, a good interval. I do a simulation and establish what the average waiting time is, but it looks good. We also need to keep our eye on the ball in terms of the time it takes to a destination when we are talking about tall buildings. So, everything falls into place and you still need to go back and check how much time does the person take to reach the destination. And that often for a taller building might be your clue for establishing the elevator speed, not just the handling capacity and the interval. The relationship between interval and average waiting time is is not understood at all, and people interchangeably use it with serious consequences. I gave you an example of Nariman point. So if you were to say that the interval and the average waiting time and Nariman point are equal, the answer is no. The interval is good because the elevator cars are smaller, but the average waiting time is much higher because people still wait. The way to arrive at your waiting time and time to destination are through simulations. And I mean, today you have excellent simulation packages. However, we still need to work on handling capacity and interval as our base. For the very simple reason, when you talk about simulations, it's not based on formula. It is based on algorithms, which could vary depending upon a software person. And again, with the problem with software is garbage in, garbage out. And in any case, we need to remember that assumptions and the right interpretations are key. Okay, so again, looking at National Building Code, we have a process which has been laid out, which I understand has now been copied by some code writers in Europe. So you go through the whole process, you establish the building, you set out the target parameters, you do the peak analysis, establish the number of elevators, then you do an optimization. You fit it into the building and see if the areas have changed. If the floor area has not changed, you're good to go. If it has changed, then you'll have to go back. So this iterative process is something that has to be always followed. I have often been asked, but we are still at the conceptual stage of the building, so we have no idea. So just give us some idea of elevators. A smaller building, possibly it will work out, but taller the building, the more difficult it is to do it because the consequences could be huge. So if you're talking about a building of, let's say, 40 floors or 45 floors, and we have to establish the number of elevators, a population difference of 150 could mean an additional elevator. On the other hand, if it's a smaller building, a population difference of 300, 350, 400 would probably not make too much of a difference. So we need to keep this in mind that there is nothing like an estimated number of elevators for a conceptual design. From the first instant, the taller the building, you have to get into detailed calculations to establish what you require in terms of elevators before you start filling it up into your architectural plans. The crucial input is population. We need to be very, very careful about it, but because if your population assumption is wrong in terms of either it being overstated or understated, both ways we have a problem. Again, if you look at the National Building Code, it does give you some guidelines, but still it's best that you understand what the building requirement is. Just NBC 2000 recommendations, like I told you, single tenancy, the minimum that multiple tenancy, the minimum you require is 10%, 10 to 15%, single tenant 15 to 25. The reason is that in the single tenancy, that diversity of arrival rates would not probably vary as much as in a multi-tenancy. In terms of your recommended average waiting time for a premium and a regular building, it is different again. Now, for a commercial building, handling capacity is, for a high end is greater than 8%, mid end it is 6 to 8, low end is 5 to 7. If those of you who know NBC 2005, we had a standard handling capacity for all the types of residential building. It was 7.5%. We did this breakup because we realized that your density for buildings in residential buildings, depending upon the level of the building, could vary. So a high-end building at 7.5% and the lower density would throw a lesser number of elevators, while a low-end building with a higher density and a higher average handling capacity would end up with more elevators than would probably be required. So we have sort of done a breakup on it. Interval again has been defined as 81 to 100. Please remember very clearly, this 81 to 100 is not your average waiting time, it is the interval. So your handling capacity has to be met, and then if you have this kind of an interval, you are sort of okay. But for a high-end building, if you have an average waiting time of more than 35-40 seconds, your resident is going to be very, very upset. Just a few more things. Those of you know destination control or conventional, one of the things that will get thrown at you as architect is saying that, okay, you don't have enough elevators, let us put destination control and take care of it. Destination control is where you input your destination outside the car. The principle is to reduce S. However, do not worry too much about it, but remember that in a destination control, your maximum car loading is less than 8, while for a conventional, your average car loading is 80%. So keep this in mind. So you do not always have an advantage with ECS. The reason why I'm saying this again is that when, as you start working, somebody says that, okay, with destination control, I'll take care of the whole thing. The answer is no, it doesn't work. Okay, we had the COVID coming up, and something that came up, and I did conduct a number of sessions during this period, and there was a request that came up saying that, okay, we need to change the national building code to account for the pandemic scenario. And my response was that if we have designed the building well from the first instant, COVID or no COVID, we do not have a problem. So if the building was designed at a 12.3% handling capacity, even the worst case scenario where you can load in only 4 people into a 20-passenger elevator, you still had a waiting time which is more than 2 minutes, which is still bad. But then if you have a constraint on the number of people that can go into the elevator, obviously you have a constraint in terms of the number of people in the building also. So if your building has been designed, COVID or no COVID, you do not have a problem. On the other hand, if your building has been designed badly, you've got a 5.5% handling capacity, you already have a problem. And with the COVID scenario, your problem becomes super, it gets escalated even that much more. So there is really no need to change the National Building Code as far as this is concerned. All we require is that we follow the National Building Code norms. Some of the errors that do happen is people ignore the criticality. I mentioned it. We miss out on population numbers. We ignore the NBC 2016 provisions. Almost every other project we come across architects who says, no, NBC 2016 is just a recommendation, so we will not be following that. Unfortunately, even when you look at it from an elevator company perspective, many of them do not understand the fundamentals. So the whole complex situation is we end up with buildings that are badly under-elevated. So designers, developers who do not allot the priority that's required for elevators, they see it as a nuisance. And combined with people from the elevator industry who also do not understand it, we end up with a very critical situation. So once you have established a number of elevators, etc., you need to do the architectural interface. What you need to do is pay attention to this slide very clearly. When you talk about elevators, number of stops and openings. So when you say, we normally have a tendency of saying if it's ground plus 7, we say it's a 7-story building. Remember, when we talk elevators, the number of stops and openings need to be clearly mentioned. So for an elevator, if it's a ground plus 7 buildings, it is 8-floor building. It is not a 7th floor building. Remember that. Dimensions of hoistway, width into depth. Width is when you focus, look at the hoistway, left to right, with your arms stretched out. If you are looking at the hoist, left to right is your width. Depth is perpendicular to where you are standing. And unlike what is mentioned in architectural drawings, where it is depending upon horizontal vis-a-vis upright, for elevators, it's always defined as width into depth. So if you are doing an X by Y, always remember that it is width into depth and not how the hoistway is positioned on your drawing. On the other hand, if you're just showing the dimensions, obviously there's no problem in it. But if you are showing X into Y, it always should be width into depth. I've faced situations where architects have given a dimension based on how it appears in the drawing. We have brought the material to site and we have realized that it didn't fit in because obviously the way it was put across was different. The pit depth, obviously it's very clear from the lowest landing to the bottom of your pit floor. People do understand that. Overhead is from your top landing to the roof of the machine room. Again, architects often make this mistake. They think the overhead is from the top of your hoistway to the machine room. That's not the overhead. The overhead is the portion from your topmost floor to the bottom of your machine room floor slab. And the travel is not the height of the building. The travel is what the elevator will travel. So from the lowest floor to the top floor. So this becomes your travel. Again, when we talk to architects, what invariably happens is they will give you the height of the building from here till here. You talk about the overhead, they will either give you from the topmost floor to the bottom of your machine room roof, or they will measure the machine room and say that this is the overhead. Remember that these are all very critical dimensions which the elevator industry as a norm across the world follow. And of course, all the dimensions that are mentioned are clear and finished dimensions. And remember that these dimensions are not fancy dimensions, but they are very clear technical requirements. Like for instance, the overhead is dependent upon the height of the car and the speed, that in the eventuality the elevator does not stop on this floor, there has to be enough space for it to decelerate and stop before it hits the roof. Not just that, we also need to keep in mind that there is a possibility that there would be a mechanic on top of the car doing maintenance, and he should not get into a position where he gets crushed. So all these are requirements which are, yes, you would have a scenario where you have the aerodrome next to your thing, and you say, no, I have a height restriction. But remember that height restriction, and if you take it and compromise it in the machine room, there will be problems as we go along. They might be able to commission the elevator, they might be able to do it. But for the next 25 years, the maintenance, there could be a problem. In addition to it, it's a safety issue. Now, when I mention safety issues, again, we do play the statistics game often. And I mean, just recently, when I say recently, I'm just talking about last week, we actually had an architect of a fairly well-known developer saying that, we need to compromise a little bit on safety. I would implore you to never ever take that kind of a situation, because there is no substitute for, you cannot substitute a dead man. A dead man is a dead man or a woman. And that is not a stance that can be taken at any cost. Safety is not something that is to be played about with. Again, remember hoistway dimensions. When we talked about width and depth, what is required is verticality and squareness. So you need to be asking, what is the contractor going to achieve in terms of verticality, the plumbness. If you can't have the elevator obviously travel in different dimensions. So your vertical lines is what you will get. So if you have a doubt about the contractor, please ensure that your hoistways are larger than what is seen in a brochure or what somebody would propose. Yes. Okay. Again, remember there are rough finish entrances. So if you want a taller door or a taller car, you need to keep in mind that there are other equipment that requires to be maintained. So if your door height is 2100, a clear opening of 2100 won't do. It will need to be more. The loads on the machine room, again, are a component, a function of the various equipment that goes in. Walls normally tends to be the dead weight, but we still need to be careful because there are brackets, there is rails, there are safety action that could happen. Similarly, a pit again has loads that we would need to be aware of. Car dimension and shape, we have an FSI-driven design process that happens. So to get that pre-FSI, they say that, okay, let us have a deeper car so that we get the entire space below. We need to remember that a deeper car is inefficient. Murphy's law will invariably apply, and the person who will get out will always have to be the person at the back, which means everybody has to troop out and then troop back in. Remember our formula of 2 into P into TP. So when we are doing the analysis, we are assuming that a person will enter in and will ingress and egress only once. But if you have a deeper car, the possibility is that there will be more number of ingresses and egresses that happen. So keep that in mind. Yes, FSI is all good, but remember the 150 crores that we did analyze and say that if your elevating is bad, the complications that are involved. The car area is defined by a formula, and the way it is that larger the car, lesser the area per person. It is not linear. The idea is to ensure that the car doesn't get overloaded, and this is a formula that is applicable whether it's in the US or it's in Japan or it's in India or in Europe. This is the formula that would come in, and these are things which would normally decide your hoistway dimensions. In terms of how you position the elevators, remember what I said. If it is 3 elevators that are required, there are 3 elevators in a group. Bear this in mind, and they have to be such that you don't need to be PT Usha jumping over hurdles to be able to approach the elevator that is comes available for you. Here, in this again from the National Building Code, and if you have 8 elevators, I would strongly recommend that on your main floor you should have it open from both sides, because if you have 8 elevators, that means the crowd is that much larger and it would need a larger lobby. But the arrangement is very, very crucial. Yes, with destination control, you have a little bit of flexibility, but the closer the elevators, the better they are for grouping. Okay, so we don't talk about grouping, and this is a building that is already existing in India somewhere, and in all the wisdom, this is how the architect has done the hoistway, and you can see from the way the hoistways have been done. First of all, 2075 into 1925. Clearly, it's a wrong way of doing it. It should have been 1925 into 2075. Incidentally, we were the consultant on this project after the building was of the 2/3 the way up. And I was told the hoistway 2075 by 1925. I made the specifications. And then I got the drawings in hand. I realized that the dimensions given to me were wrong. So error number 1 in the way the dimensions have been given. Error number 2, this is a 40-floor building. And if you have a hoistway of 1825, eventually you will effectively get a hoistway which is about 1750. And in this case, the construction accuracy was so bad that 1825 actually became 1600. 1600 is what we managed to get as an effective hoistway size. It's obvious again that not too much thought had gone into what was required in terms of elevators, because these 3 elevators, grouping them together is difficult. If you look at the hoistway sizes again, you could see that these have been all fixed in to accommodate what is convenient to everything else that has been designed. And I keep saying that, after everything was designed, suddenly somebody decided that, okay, we need to have elevators too, and then they put it in wherever they could fit in, and that is how these dimensions were achieved. This is again a building which we refused to work on. This is how the drawings were given to us. This is for a 50-floor building. 1.95 will obviously turn out to be 1.75, and the way in which they had given me the drawing and the way they were sort of constructing the building, we realized that there wasn't too much of seriousness, and obviously for a 50-floor building, this was grossly inadequate in terms of elevators. This building has been complete, and I keep sort of a tab on it, and I understand the residents are very, very, very upset with the developer, because they invariably have problems with the elevators. Capacity is less, your hoistway sizes are less, the elevators are inadequate, and they really do not have a calculation for deciding on these number of elevators. So tall buildings, it's a very tall perspective. Always bear in mind that the complexity is exponential. I had a developer who they have done a lot of 10-story and 15-story commercial buildings, and now they are doing a 42-floor commercial building somewhere in India. Finally, we had to excuse ourselves from the project, because their only way of looking at elevators was saying that, okay, in the 10-story building, we put in 3 elevators. So 42-floor buildings, we should be okay with 9 elevators, or 9 or some 12 elevators. While our calculation was showing that you required 20 elevators. His 10-floor building he had done at 1.5 meter per second. So he said for the 42-floor building, we should be okay with 4 meter per second. Our requirement was a minimum of 6 meter per second. So we need to recognize that the complexity is exponential. And an example that I would give is, if you had to go from here to Delhi, you would either take the Rajdhani or you would take a plane. You would not venture out in a car, or you would not venture out in an auto rickshaw. Unfortunately, in many of these instances, this is how we approach buildings. We need to recognize that as the building grows taller, your core will eat into the building. Burj Khalifa, I understand that the core for elevators and the services accommodate takes about 50% of your footprint. This is something that you cannot do anything about. The taller the building, the more you require in terms of elevators. And what the developer requires in terms of larger floor space and what you require in terms of elevators is conflicting. And remember this formula. So as the building grows taller, you would need to look in terms of a fast train, local train, vertical zoning. I mean, using the fast train, local train. So if you had to take a plane to Delhi, you would take a road transport to get to the airport, and you would not expect the plane to come to your residence. Or if you had the Rajdhani, which starts from Bombay Central, you would go to Bombay Central using some other means of transport, and then you would go. So this is typically what would happen. You would not have elevators serving all the floors. I'll just give you a few examples of what could happen. You would internally split the elevators. You would have sky shuttles. Rather than just look at this, what I would probably do is show you a few examples of what could happen. You could have sky lobbies. You could have elevators which are for upper floors or even lower floors. You could have stats zones, which exactly is what happens in Merriman Point or Cuff Parade today, which is not a great idea because what people will do at the lower floor is they will push both the buttons and decide to walk one floor below. Some of the equipment that is available is a double-deck elevator, which is both floor elevators attached to each other. Typically, if this has to work, the floor-to-floor height has to be fairly exact. Though you do have an option of flexible double deck, you need to remember that there is a time involvement. The moment you have this kind of flexible, it takes even that much more time for your stops and starts. There is something else called a twin, but unfortunately, the twin is two different machines in the same hoistway. Unfortunately, it is still a single vendor who has got it, so it has not become very popular. And in addition to that, there are some violations of the code which happen because it has to be electronic safeties and your standard safeties do not always work. Okay, some of the things, single deck shuttles, we talked about things. So for taller buildings, some of the thing is single deck local, double deck shuttles, single deck locals. Then instead of going just through it, let's just go at the examples. So Sear Towers, for instance, so suppose you want to go to the 87th floor. So what you would do is you would take these double deck elevators, which would express you to the sky lobby, which is on the 67th and 66th and 67th floor. And from there, you would transit into 80th floors. You would transit into this mid-rise, and from there, you would go to your particular floors. We do come across numerous situations where the architects know, but the client doesn't, the tenant would not find it convenient to transit. But we need to remember, further the distance, more important it is to transit that you get the advantage of speed and you reduce the number of stops. So if you look at the Petronas Tower is a total double deck alternative. So if you had to go, let's say, to the 61st floor, you would express to the sky bridge here, and then you would take the elevator, the lower or the upper elevator to go to the floor you require. So when you have this kind of a situation double deck, you obviously will need alternate means to travel from your lower floor to the upper floor because the upper floor car will not come to the lower floor, double deck, obviously. So there would be escalators that would also need to be provided. This is the United Overseas Bank. Again, so if you want to go to the 56th floor, you would take the express till here, and then you would transit to these elevators and you would go to the 56th. And this is, here, if you want to go to the 36th floor, you would take this and then you would take these elevators. This arrangement is not something that is preferred a lot because of the very simple reason that going down, often people feel bad that, I've had to go up to go down. But then sometimes this is the only thing that works out. Shanghai Financial Center, again, is a double deck alternative where you have to take double decks to get to your particular floor, and then from there again transit into double deck elevators. So speeds, there's always a problem in terms of acceleration, deceleration. So there's a limit. It is not like we can have any speed. Obviously everybody wants to do speed, and today the fastest elevator is 20.5 meter per second. And remember, it's only in the up direction. And followed by that, the 16.83 and 10 meter per second elevators have been in existence for a very long time. Even in the Burj Khalifa, you don't have a single elevator that goes through all the buildings. There's always a transit for everything. So there's no elevator that goes through all the floors. And one of the primary reasons for it is the weight of the ropes. For Burj Khalifa, some of the elevators which go the longest distance, the weight of the rope is far in excess of the weight of the car. So when we again talk about buildings, we talk about construction accuracy. Always remember how critical that is. Squareness has to be considered. Wind tunnel effect. What happens is the higher the speed, and if you have a closed hoistway, you have a problem. So always either provide for larger hoistways, significantly larger hoistways, or ensure that the intermediate walls are not there. The partition walls are perforated. Partition walls are not there at all, and you just put in steel beams for your brackets. In any case, remember, do not refer to standard hoistway dimensions. Depending upon the building, for a tall building, you will need to get into exact details. Other technical things that you need to consider: the building sway, you need to ask about that. Earthquake, what is the earthquake zone? You need to be looking in terms of what the installation methodology is. You need to plan on what it is. It's not just like a smaller building. You really will need to plan on how you do it. Building floors, the finishes. If you're going to be doing wet cladding with architraves, it's going to be even that much more difficult for a taller building. So if you're going to do cladding on, let's say, on the 50th floor, remember that slurry goes all the way down. And I would strongly recommend that, it should be dry cladding, that you look at that kind of situation. Redundancy requirements always need to be kept in mind. The taller the building, the more complicated. Even regular maintenance takes that much more time. So your elevators will be shut down for that much longer. Security again becomes a concern. And remember that despite all your protection equipment that you have for an elevator, there's nothing that can be done to stop tailgating. Okay, so fireman evacuation elevators, I'll rush through this. I will not rush through this. The rest part I'll rush through. Remember always that elevators are not waterproof or fireproof. I'm starting with waterproof. Water will kill it first. But because of the fire-resistant doors, it is fireproof to some extent. And an architect's role to ensure that the elevator is protected from water, fire, and smoke. And again, if you look at the National Building Code, Part 4, they sort of give a good idea as to how it should be like. Again, a question that will come up, and probably over the next couple of sessions that you do, there will be this question that will come up about hoistway pressurization. So if you do look at the National Building Code again, this is Part 4, not Part 8, Section 5A and 5B. It says that in the eventuality you don't have an elevator lobby, that the the lift opens up into an open area, or an air-conditioned building where it's an open corridor, like it opens up into a flat, then you might need to consider hoistway pressurization. Otherwise, hoistway pressurization in many ways is a superfluous requirement, because what will first impact your elevator is the water, then the fire, and the last thing is the smoke. Unfortunately, most of the buildings, the design focus is on pressurizing of the hoistway, which, like I said, is superfluous, in addition to which it has a potential of creating problems. And one of the requirements that we have for hoistways is to have a smoke window for extraction of smoke in the eventuality there is a fire inside the hoistway. Now, if you have the smoke window and you have the cutouts in the machine room, I wonder how you will pressurize that hoistway. So in many ways, you do put in a fan, but do you really manage to pressurize the hoistway? My answer, I'm not an expert in it. My answer is no. And I've talked to experts who say that, yes, it is a problem. Now, in the eventuality, this elevator is your fireman's lift or your evacuation lift, and now you've pressurized the hoistway. We also do have a possibility that this elevator could get handicapped by effect of the pressure that is being thrown in. So you could have a situation where either the fan works or the car works, because like a pressurization fan is throwing in air into the hoistway while the car is trying to push air out of the hoistway when it is moving up and down. We also had seen situations where, because of the pressure difference, the doors would not close. So keep this in mind. There are lots of experts, and I've been talking about this for about more than 10 years with various experts. At the panels and the discussions, they all agree to what I'm saying. But finally, when the designers come in, they say, no, we have to put in pressurization fans. And if you look at the National Building Code, it is very clear. It vindicates my stand in terms of the fact that pressurization of the hoistway is something which is superfluous, unless you have a specific requirement. And again, the other thing that would vindicate it is the Burj Khalifa, not a single hoistway is pressurized. Standards and codes. We do have standards and codes. In many ways, our standards, we do have a tendency of saying that Indian standards are weak. Except for the escalator standards, in many ways, our standards are fairly adequate and fairly strong. There are international standards, ISO 8100, EN 81, EN 115, the European norm. You've got the Japanese industrial standards, you have the American standards. I think barring the American standards, probably in many ways, our elevator standards are more stringent than the international standards. The National Building Code we have also is a fairly fine document. I'm not saying that because I'm the convener. The section on planning for buildings is something that you will probably find only in the National Building Code and nowhere else. The closest you will find would be SIPSI Guide D, nowhere else. So to sort of conclude, it's essential that as architects, you recognize that elevatoring is not based on thumb rules. This is a very crucial science. And, it's not just that you put and say that, okay, let me put in so many elevators. Remember that, I mean, like Gina Bani, for instance, this book is, she has researched for more than 50 years, 50, 60 years. This is her second edition of this particular book, but her third book on traffic analysis. George Takosh, the late George Takosh, who's passed away, he has spent more than 60 years of his lifetime on elevators and traffic analysis. We have the National Building Code. Recognize the criticality. Remember that you will make or break that building. That once you have done the wrong elevators, that building is doomed. The examples that I gave you are buildings which the architect doesn't even want to refer to because he knows that the building is losing tenants. Tenants are walking out of the building because of the long waiting periods. Of course, if tenants walk out of the building, the problem is resolved because your population is less, your average waiting time improves. But then obviously that is not the intent of your building. And react in time. If you have not set this right when you are at the drawing board stage of the building, the moment it gets into a building approval plan or situation like that, it's too late. There's really nothing that you can do after that. So we come across these kind of buildings and they always say, now what do we do? I say that, well, possibly the only thing that is left is the old Indian rope trick. Of course, demolishing the building is the other alternative, demolish and rebuild with a better plan. Otherwise, the only alternative that you have is probably the old Indian rope trick. So with that, I will stop and open it up for questions.
Thank you. Thank you, Mr. Mathew. Any questions from the student side? Yeah, Abdul. Yeah, Kadir.
Hello, sir.
Yes, sir.
Sir, my name is Abdul Qadir. So my question is, you talked about the speed of the lift and how the speed should be convenient in terms of the passenger. It should be fast, but should also have some sort of convenience when you're traveling. So what about the acceleration of a lift when it starts and it achieves, for example, a speed of 10 meters per second? And what kind of acceleration? Because I think that stage will be more critical than the speed when it's uniform.
The acceleration. I mean, I will just put that back in on that slide back up. So your maximum acceleration is 1.5 meter per second. You also need to keep in mind that the change of acceleration also makes a difference.
Okay.
1.5 is what probably the Americans will handle or the Europeans will handle. We Indians will not be able to handle it. 1 meter per second squared or 1.2 is what Indians we can manage. The Japanese, for instance, will normally never go above 1 meter per second squared in terms of acceleration. So what you pointed out is very right.
Yes.
And I mean, you know, I've got motion sickness. So when I go for inspecting elevators, even at 0.8 meter per second squared, when I go up and down a couple of times, I have to sit down because I feel nauseous. So what you're saying is very, very right.
Yes.
And the key here in all this is the rate of the change of pressure.
Okay.
So like an aircraft also, the reason why you have it is the change of pressure.
Yes, sir.
So if it had been gradual, the change of pressure, like if people who go to climb a mountain, they go gradually up. They don't rush up.
Yes, sir.
Right. So it is acceleration, which is, I mean, not the acceleration on its own, it's the acceleration impacted by pressure. So if the acceleration, suppose it had been horizontally, you would not have had the same issue.
Right. Yes, sir.
Right?
Yes, sir. Thank you, sir.
You're welcome.
Yeah. Any more questions? Sir, I have a question regarding nowadays for the tall buildings, we have so many panoramic lifts. So can you highlight on the features of those panoramic lift for tall buildings?
Yeah. So the tallest panoramic lifts, I believe, have been put up in Dubai. So some of the issues that happen is, one, we talked about acceleration and the impact of the change of pressure. Now, if you are in a closed point, your impact of speed is going to be less because you can't see out. But if you can see out and the speed is going in, it's very uncomfortable for passengers. Again, I talked about myself as a person who has motion sickness. And I mean, it's pretty hilarious also that, despite being the elevator business, I also got a fear for heights. There are many people who have a problem in having these panoramic elevators for tall buildings. That's one aspect. Second is, if it is a panoramic elevator that is exposed to the outer surface, you have claddings outside. You will have a facade that is put up. And now these facades will have horizontal members to support the structure. So as you're going up, the supports start cutting your view. And depending upon how fast the elevator is, the more of an impact it has on the users. So though it is good and it is fine, I know many people who have a problem in these panoramic elevators to use as a regular elevator. So if you're going to be putting up a panoramic elevator for a tall building, panoramic elevator or elevators, always bear in mind that this has to be over and above your regular elevator that's available. Or in time to come, you'll probably have to put in a black cloth or something like that and close it up because users will have a problem. So the ones in Dubai, for instance, they have regular elevators also, which ensure that for somebody like me, I'm comfortable. Does that answer your question? Hello? Yeah. So though it looks nice, also need to keep in mind the usage situation. What is the impact on users? I mean, this is not supposed to be a a fun park, right? It is not supposed to be a theme park.
Right. Agreed. Totally agreed. Total psychology and everything is concerned for that.
And don't forget, how are you going to maintain the facade and how are you going to clean the facade inside?
Exactly. Right.
I mean, I give this use whenever somebody wants a glass elevator. I keep saying, Salman Khan can take his shirt off and show his 6-packs or 8-packs or whatever it is, but that requires a lot of effort to maintain those 6-packs and 8-packs. Now, if you don't have that, for heaven's sake, please don't take off your shirt. I mean, that's what I'm in a glass elevator.
True. Very true.
You look around the glass elevators and then you find cobwebs and you find dirt and you find that and then it's over.
Right. Any more questions? Any more questions from students and faculty?
I guess it is kind of intense. Kind of.
Vinit sir, your voice is breaking.
Yes, I said that it is quite intense for a faculty and the students both come up with a kind of. I guess those kind of questions are going to be bound to come to us,
Sir?
and I guess we would forward that to. Hello.
Yeah. Sir, we can hear you now.
Yeah, so that's why I said that the lecture was quite intense. It was more than what we have been talking to our students, and because whatever we deliver to the students, that's what we normally been kind of venture and explore as our kind of knowledge system. So the kind of outlook Mathews sir has given, I guess that has created lots of questions and lots of inquiries in our mind for both faculty and a student. I guess those will start coming up in a fine print in some time. It will take some time to come up with a kind of a very correct, articulated inquiries. And I guess we will forward those inquiries, Mathews sir, and we will start getting those answers if we find.
It is a commitment that I have that if you're willing to listen, I'm willing to talk about my experience and what knowledge I have.
Yeah, absolutely. So what happens then? That's what I said. That once we start, like lots of things, we have been always as an architect, we have been the as what you have talked about the NBC, the banks of lifts, various banks of lift which is been provided, waiting time and the basic calculation which has been given to us. But there are lots of other finer aspects as a consultant you have been putting to us, which is also us for as faculty also, it is important for us to get into that exploration and trying to understand. And it's our job as a faculty to kind of simplify and give back to the students so that they can absorb that and then able to apply there in their design process. As what you rightly said, that if we actually plan it correctly as an architect, lots of anxieties from the consultant sides are going to be kind of reduced in the kind of meetings to come. So I guess it is important that this collaboration is a kind of milestone towards that, because that is how this is going to affect positively for our fraternity. So it is important that we both as a faculty and students start understanding these things, trying to upgrade, because many times what happens is that as a faculty also we have been delivering the similar kind of things, and lots of things have been changing in industry. So this interface is going to be important, where the newer technologies, newer concerns which has been posted into the industry also has been tabled on the academia, and that is how we will be able to take it further than that.
It's my commitment. Whenever you want me, I'll be there. Don't worry about that.
Yes, sir. And we will definitely bother you.
It'll be a pleasure always.
Yeah, because I guess it was difficult, I guess, to compress so much into 1.5 hour lecture. It is not possible because each aspect will take an hour of discussion. Again, I understand your anxiety, how you have able to compress the whole situation into this small lecture. It is not easy, but at the same time, this is the kind of start which is required, because these are the kind of questions and the kind of overwhelming reactions which happens both for the faculty and this, that this much has to be addressed, this much has to be understood before you get into a planning situation. So it is very important for us to open up this array of aspects which you have given to us. I guess more exploration will happen and more inquiries will come, and I guess as what you have said, you have committed to that, we will have more of these interaction in future also.
Sure.
Sure. Thank you, Mr. Mathew.
Thank you very much.
And even I think thank you, Vinit sir. Thank you, Chandavarkar sir. I think Girish sir and Anuja ma'am is also here. Thank you very much for their support. Anyone wants to talk about this? Okay. So thanks, Mr. Mathew. We will definitely come back to you later on with some more questions and some more sessions. Thanks for your contribution. Thanks a lot.
A pleasure.
Okay. Thank you, guys.
Yeah. Have a nice weekend.
Gauri sir.
Yeah. No, I'm quite overwhelmed with the whole process. As Vinit said, that we've never been looking into such a process or in such a way of teaching. So we will come back, sir. Thank you again for tolerating our silence.
No, it's okay. I mean, it's a circumstances. What do you do?
Yes, but I'm sure that this whole series will bring in some value in whatever we're doing, and let's take it ahead. I should thank Girish and Anuja for establishing this whole series and opening our eyes and minds and application to these new architecture solutions. So we'll definitely go ahead. Thank you so much.
Thank you, sir. Thank you. Shall we conclude?
Yeah. We'll conclude and we'll meet again later.
Sure. Thank you. Thanks a lot once again, everyone for participating.
Thank you, students, also for patient listening. I guess more queries has to come out. Maybe it's not done now. but it's important that you put up those queries to various technical faculties or otherwise, so that we can forward them correctly to this experts, and then we'll get a feedback. And whenever it's required, as Mathews sir has said, that he's committed to do that. And I guess last lecture also, Gautam sir and Anuja said that we are committed to whatever further sessions required for that further explanation. So I guess it's now our duty as a student to pose these kind of questions to this panelist, so that we have this interaction on a more frequent basis. And I guess that will create a better learning platforms for all of us. That is what I would tell you. Thank you. Thank you, Parikshit, for conducting this event. It was important that you were taking that initiative for the college and doing that effortlessly.
Thank you, sir.
Thank you very much.
Thank you, Matthew, sir.
Thank you.
Have a great day.
Have a nice weekend. Stay safe.
Thank you, sir. Thank you.
Same to you.
Same to you.
Bye.
Bye.